Hi everybody, welcome back to Quantitative Reasoning. Today we are in section 11.4 and we're going to be looking at some fundamentals of probability. We'll talk about two different types of probability in this section. We'll look at theoretical probability and empirical probability. Okay, the first thing you need to know is that probabilities are assigned values from 0 to 1. The closer that a probability is to 1, the more likely it is that the event will occur. And the closer that a probability is to 0, the less likely that the event will occur. So you can see here, if something has a probability of 0, then it is impossible. If it has a probability of 1, then it is guaranteed certain. If it has a 50-50 chance, it has an equal chance of happening or not happening. So notice that in percent form, we would say the probability is between 0% and 100%, but usually we work in decimal form, and so we talk about the probability being between 0 and 1. So you'll never have a probability that's greater than 1, because if it has a probability of 1, it's guaranteed to happen. And you'll never have a probability that's less than 0, because if it has a probability of 0, it's impossible and it can't happen. Now let's get a little bit of probability vocabulary. So we need to know what some of these words mean when we see them in a problem. Any occurrence for which the outcome is uncertain is called an experiment. I don't want you to think of an experiment like a scientific experiment, but just something where the outcome is determined by chance. For example, flipping a coin is an experiment because you don't know if it will come out heads or tails. Rolling a die is an experiment because you don't know which number will come up, so that means the outcome is uncertain, so that makes it an experiment. Now, the set of all possible outcomes of an experiment is called the sample space of the experiment, and we always denote it by S. So S for sample space. And then an event denoted by E is any subset of a sample space. So set E will always be a subset of set S. Now if you take the probability for every possible outcome and add all those probabilities together, they always have to add up to 1. And we use theoretical probability when we're in situations where all the outcomes in the sample space are equally likely and all the outcomes are known. So if we have those two conditions met, we can use theoretical probability. Now I'm about to show you how to calculate theoretical probability, and it's not hard, but this definition right here looks a little daunting. So let's kind of remember what some of this notation means. Do you remember from chapter 2 where we talked about cardinality and we had this notation N of E? Remember, this stood for the number of elements in E. And so right here we've got the number of elements in S. Okay, so when we're trying to calculate the probability of event E, we need to know how many outcomes are possible for event E. In other words, how many elements are in set E. And then we also need to know how many elements are in the sample space, which is the set of all possible outcomes. So when we know the number of elements in E and the number of elements in S, then we can calculate the probability of event E. So that's what this means right here. The probability of event E is the number of outcomes in set E divided by the total number of possible outcomes, which is the number of elements in set S. So the probability of event E is just the number of elements in E divided by the number of elements in S. And because E is a subset of S, the number of elements in E can never be more than the number of elements in S, and that means that this fraction will always be a number between 0 and 1. So we can calculate probability in this way whenever we have a situation where all outcomes are known and all outcomes are equally likely. So that applies to games of chance, things like rolling dice, buying lottery tickets, playing card games, roulette. And again, all of these types of things are included with theoretical probability because in theoretical probability, all the outcomes are known and all the outcomes are equally likely. So what we need right now is a good example. So let's look at example 1 together. It says a die is rolled once. So we can assume this is a standard 6-sided die. And of course, rolling the die is what we call an experiment because we don't know what will be the result of rolling the die. But we do know all of the possible outcomes, and we know that each outcome is equally likely. So that makes this a perfect application for theoretical probability. Let's go ahead and list the elements of the sample space. Now remember, the sample space is just the set of all possible outcomes. So when we roll a standard 6-sided die, the possible outcomes are that we will either roll a 1, 2, 3, 4, 5, or 6. So this is the sample space. Now the problem says, find the probability of rolling the following. And each of these things that we are going to find the probability for, each of these is an event. And the possible outcomes in the event will be a subset of S. Now, as we work with each one of these events, we will call it event E, just because E is easy to use because event starts with E. Okay, so in part A, event E is the event of rolling a 3. So what we want to do is list all of the outcomes that fit this description. And so the set E will be the set that includes 3. 3 is the only outcome that is suitable for this event, okay, because they asked us to find the probability of rolling a 3. So when we get ready to calculate the probability of E, we'll write probability of E equals the number of elements in E divided by the number of elements in S, and the number of elements in E is just one element. The 3 is the only element there, so the number of elements in E is 1, and the number of elements in S is 6. And so the probability of rolling a 3 is 1/6. Okay, let's move to part B. And here, event E is the event of rolling an even number. And so this time, set E is going to include any outcome from the sample space that fits the description of being an even number. And so those outcomes would be 2, 4, and 6. Okay, now when we calculate the probability of this event E, that would be the number of elements in E divided by the number of elements in S. This time there are 3 elements in E, but still 6 elements in the sample space. So this time the probability of E is 3/6, which will simplify to 1/2. Now, I think probably everybody knows how to simplify a fraction like this, because if the two numbers can both be divided by the same thing, then you divide both numbers by that same thing, and what's left is the simplified fraction. So in this case, both of these numbers can be divided by 3. 3 divided by 3 is 1. 6 divided by 3 is 2. And so the probability of rolling an even number is 1/2. Now, I hope that you're comfortable simplifying a fraction like this, but just in case you ever want the calculator to simplify a fraction for you, let's cut to the calculator and take a look at that. So I just want to make sure that everybody realizes that this calculator will handle fractions for you, and the button you need for fractions is this A, B over C button right here. And so if we enter a fraction like 3 fraction bar 6 and we press equal, it will simplify the fraction for you. If you enter a fraction that cannot be simplified, like 7 fraction bar 8, then of course it just gives you the same fraction. But if the fraction can be simplified, the calculator will do it for you. Now, I also want to show you one other thing. If you forget about the fraction button for a minute and you use the divide key, you would have 3 divided by 6, and it will go to decimal form, but you can still get the calculator to convert this to fraction form for you if you use this function right here. Do you see above the PRB button, it says F to D. That is fraction to decimal conversion. So right now it's in decimal form. If I do second f to d equals, it converts it to fraction form. And if I wanted to go back to decimal form again, second f to d equals, and I'm back in decimal form. Okay, now moving to part C. Here we have the event of rolling a number less than 5. So in this case, set E is the set of all numbers from the sample space that are less than 5. So in this case, E contains 1, 2, 3, 4, and that's it because these other two elements from the sample space are not less than 5. Okay, now the probability of rolling a number less than 5 is still the number of elements in E divided by the number of elements in the sample space. So there are 4 elements in set E, so we'll say that's 4 divided by 6 elements in the sample space, and we have 4 over 6, and both of these numbers can be divided by 2, so when we do that, this fraction simplifies to 2/3. And then looking at part D, we want to find the probability of rolling a number less than 10. Now this time, set E is going to include all 6 outcomes from the sample space because all 6 of these outcomes are a number that is less than 10. So when we calculate the probability of rolling a number less than 10, that's going to be 6 outcomes divided by 6 elements in the sample space, and of course 6 divided by 6 is 1. And so you can see that when we roll a regular 6-sided die, we are absolutely guaranteed to get an outcome that is less than 10 because all the outcomes are less than 10. So this is why we say that the probability of a certain event is 1. Whenever all of the outcomes from the sample space are also included in the event you're finding the probability for, you're going to end up with the same number in both the top and the bottom, and any non-zero number divided by itself is 1. Okay, let's keep going with example 1. So I'm going to just recopy our sample space here so we can still see it. And in part E, they've asked us to find the probability of rolling a number greater than 6. Okay, this time when we try to list the elements of set E, there are no elements in the sample space that are a number greater than 6. So set E is the empty set. In other words, it has no elements. So when we calculate the probability of E, it's the number of elements in E, which is 0, divided by the number of elements in S, which is 6, and 0 divided by 6 is 0. So you see that when a probability equals 0, it means that the event is impossible. It can't happen. Now for the rest of these, if you would like to pause the video and try them on your own, this is a good time to do that. And now I'll go through them with you. Okay, so in part F, we are asked to find the probability of rolling a 2. So set E will contain only one element, and that is the 2. So the probability of rolling a 2 is going to be the number of elements in set E, which is 1, divided by the number of outcomes in the sample space, which is 6. So the probability of rolling a 2 is 1/6. And for part G, we are asked to find the probability of rolling a number less than 4. So the first thing to do is list all the elements in set E. So we look at the sample space, and the numbers that are less than 4 are 1, 2, and 3. And then the probability of rolling a number less than 4 would be the number of elements in set E divided by the number of elements in the sample space, and 3/6 simplifies to 1/2. And for part H, the probability of rolling a number greater than 7, first we need to list all of the outcomes in the sample space that are greater than 7, and of course there are none, so set E contains 0 elements. And then the probability of rolling a number greater than 7 would be the number of elements in set E, which is 0, divided by the number of elements in the sample space, which is 6. And so the probability of rolling a number greater than 7 is 0. Okay, dice are not the only things that we can use to calculate probabilities. We could also work with a standard deck of cards. Now I know that not everybody plays cards as often as we used to when I was growing up. So let's look at what's in a deck of cards and how the deck is made up. So a standard deck of cards contains 52 cards, and the cards are divided into 4 suits. The suits are hearts and diamonds, which are red, and clubs and spades, which are black. So you can tell what suit you're working with by the shape on the card. I'm going to go ahead and label these for you. This top row is the suit of spades. So look at that shape, and that's what the spades are. The second row is the suit of hearts, obviously a heart shape. The third row is the suit of clubs, and the fourth row is the suit of diamonds. So the hearts and the diamonds are red, the spades and the clubs are black. Now within each suit, you have the same 13 cards. So each suit has 13 different face values. Instead of a 1, the first card is called an ace, and then you've got a 2, 3, 4, 5, 6, 7, 8, 9, 10, and then there are 3 more cards, the jack, the queen, and the king. Okay, so that's a total of 13. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. The jack, the queen, and the king are called the face cards, or sometimes they're called picture cards. But altogether, the jack, the queen, and the king are the cards that have a face on them, and so they're called the face cards. Okay, so now let's look at example 2, and let's calculate some probabilities based on a standard 52 card deck of cards. So it says you are dealt 1 card from a standard 52 card deck. Find the probability of being dealt in part A, a king. Okay, so we need to know how many kings there are in a deck and how many cards there are in the total deck. So when we look at the deck, of course, you can see there is a king in each suit. So there are 4 kings in our deck. So the probability of getting dealt a king is 4 divided by the number of cards in the deck, which is 52. Now 4 over 52 does reduce because both of these numbers can be divided by 4, and so this reduces to 1 over 13. And in part B, we're asked to find the probability of being dealt a heart. Okay, so we need to know how many hearts there are in the deck. And we know that the hearts are one of the suits, and so there are 13 cards in this suit, these 13 cards right here. And so the probability of being dealt a heart would be 13 divided by 52. Again, both of these numbers can be divided by 13, and so when we simplify this fraction, we'll have 1/4. Okay, part C. Let's find the probability of being dealt the king of hearts. Now, the king of hearts is one particular card. There's only one king of hearts. These other kings are king of spades, king of clubs, and king of diamonds. So there's only one king of hearts in the whole deck. So the probability of being dealt the king of hearts is 1 divided by 52. And then for part D, let's find the probability of being dealt an ace. So you can see that there are 4 aces. So the probability of being dealt an ace is 4 divided by 52, which simplifies to 1 over 13. For part E, it says find the probability of being dealt a red card. So we need to know how many red cards there are in the deck. Well, there are 13 hearts and 13 diamonds that are all red. So there are 26 red cards in the deck. 13 plus 13 is 26. So the probability of being dealt a red card is 26 out of 52. And so 26 divided by 52 simplifies to 1/2. And then for part F, find the probability of being dealt a red king. Now, the kings are right here. 2 of them are red. So the probability of being dealt a red king is 2 divided by 52, which simplifies to 1 over 26. Notice that in every case, every answer that we've gotten has been between 0 and 1. They're all fractions between 0 and 1. And because 1 represents the probability of a guaranteed event, you're never ever going to calculate a probability and come up with an answer that's greater than 1. If you do, then something has gone wrong. Now let's look at example 3 together. This is still a theoretical probability. So the problem says, the table shows the 4 possibilities for a child whose parents each carry one cystic fibrosis gene. Capital C represents a person who does not have the disease and does not carry it. Capital C, little c, and little c, capital C represent a person who does not have the disease but does carry it. And little c represents a person who both has the disease and also carries it. So this is called a Punnett square, right? And I bet you remember this from high school biology, most of you. But whether you've seen one before or not, it doesn't matter, because the problem explained to us here what each set of letters represents. So when we look at this table, the first parent has one gene that does not carry the disease and one gene that does. The second parent also has one gene that does carry it and one gene that doesn't. So the four possibilities that can come from this are capital C, which means the child does not have the disease and does not carry it. Capital C, whether the little c came from the first parent or the second parent, it doesn't matter. If they have one small c and one capital C, it means that they carry the disease, but they don't actually suffer from it. They're not sick. And then if both parents pass on the little c gene, it means that the person both carries the disease and has the disease. So this outcome is the only time that we get a sick child. Okay, so the question is, if each parent carries one cystic fibrosis gene like we see in the table here, what is the probability that their child will have cystic fibrosis? Okay, out of the four outcomes, there's only one where the child will actually have the disease, and that's little c. So the probability that the child actually has cystic fibrosis is 1 out of 4 possible outcomes. So that probability is 1/4. And here's part B. If each parent carries one cystic fibrosis gene, again, like we see here in the table, what is the probability that their child will be a carrier of the disease who is not actually sick? Okay, that situation is represented where there's one capital C and one lowercase c, and so there are 2 of those, and so the probability that the child is a carrier but not sick is 2 divided by 4, which reduces to 1/2. And here we are at example 4, and so we're going to work with coins now. We've had dice, we've had cards, now we've got coins. And this is still theoretical probability because when we toss a coin, all outcomes are known. It's either heads or tails, and both outcomes are equally likely. So theoretical probability works great here. And the problem says a fair coin is tossed 2 times in succession. The set of equally likely outcomes is heads, 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 tails, tails, heads, or tails, tails. Find the probability of getting each of the following results. Okay, so let's kind of review our vocabulary here a little bit. The act of tossing the coin twice is an experiment because we don't know how it's going to turn out. The list of all the things that can happen is called the sample space. So this set of 4 outcomes is our sample space. And then in the problem, we're asked to find the probability of each of these events. So for each question, we will figure out how many outcomes belong to this event, and then we'll calculate our probability. Okay, so for part A, they've asked us to find the probability of getting 2 heads. So we will call this event E. So we want to list all of the outcomes that are part of event E. So when you look back up here at the sample space, there's only one outcome where 2 heads are listed, and that is the outcome HH. So that's the only one, and so now when we calculate the probability of E, it's the number of elements in E, which is 1, divided by the number of elements in our sample space, which is 4. So the probability of getting 2 heads is 1/4. For part B, we're supposed to find the probability of getting a head on the first outcome. So remember, we're tossing the coin twice, and we want to know the probability of getting heads on the first outcome. So let's look back at our sample space and figure out how many of these outcomes fit this description. So again, we'll call this event E, and the outcomes where we have a heads on the first outcome are HH, and HT, so that's 2. So the probability of event E is 2 divided by 4 elements in the sample space, and 2/4 reduces to 1/2. For part C, find the probability of getting at least one tail. So again, let's call this event E. So I want to list all of the outcomes from the sample space that fit this description. So at least one tail, that would be the HT, the TH, and the TT. So each of these has at least one tail, and that's 3 elements. So the probability of getting at least one tail is 3 divided by 4, and that doesn't reduce. So the final answer here is just 3/4. And then for part D, find the probability of getting different outcomes on each toss. So if this is event E, the elements from the sample space that fit this description are the HT and the TH. And then when we calculate the probability of event E, that would be 2 elements divided by 4 elements in the sample space, and 2/4 reduces to 1/2. So I want to emphasize again that every time we calculate a probability, we come out with some value between 0 and 1. If the event is impossible, we say it has 0 probability. If the event is guaranteed, we say it has a probability of 1. But if it's something that might happen or might not, like each of these events, then the probability is somewhere between 0 and 1. Okay, here is example 5, and this is another example of probability with dice. So it says a pair of fair dice is rolled. The sample space is shown below. Find the probability of rolling each of the following over here. But first, let's look at our table here. These are all the outcomes you can have when you roll 2 dice at the same time. So you could have a 1 and then a 1 and then a 2, and so on, up to 6 and 6. But how many different outcomes are there? Well, it looks like 36, because the first die has 6 different values it can be, and the second die has 6 different values it can be. So together, remember what we learned in section 11.1, there are 36 different results that we can get from the pair of dice. Okay, so part A, find the probability of rolling 2 even numbers. Well, let's just go back to our sample space and let's use it to find all of the outcomes where there are 2 even numbers. On this first row, the first die is always a 1, so there are no outcomes on the first row that fit this description of having 2 even numbers. But look at the second row. Right here where we have 2 and 2, that's 2 even numbers, 2 and 4, or 2 and 6. So we got 3 outcomes on the second row. Then for the third row, the first die is always a 3, so there aren't any outcomes on this row that fit our description of 2 even numbers. But on the next row, we have 4, 2, 4, 4, and 4, 6. And then we skip the row where the first die is a 5, and then on the last row, the 6, 2, 6, 4, and 6, 6 each have 2 even numbers. And so there are 1, 2, 3, 4, 5, 6, 7, 8, 9 of these outcomes where there are 2 even numbers. So the probability of rolling 2 even numbers would be 9 divided by 36. Remember, 36 total outcomes in the sample space. Now this is a fraction that can be reduced. Both of these numbers can be divided by 9, and so this will reduce to 1/4. For part B, it says find the probability that we roll 2 numbers whose sum is 5. So let's go back to our sample space and find all of the dice where the 2 dice add up to 5. Right here, 1 plus 1 is 2, so that's not enough. Then if we go down 1, 2 plus 1 is 3, still not enough. On the next row, 3 plus 1 is 4, still not enough. On the next row, 4 plus 1 is 5. So that's one of our outcomes where the sum is 5. Now we can find the rest of them really easily by going in a diagonal line. So if we go up here, 3 plus 2 is 5, 2 plus 3 is 5, and 1 plus 4 is 5. And you can see that those are the only ones that work, because to the left of these 4 that we have circled, all of these sums are too small, and to the right of these 4, all of these sums are too large. So these are the only 4. So the probability of rolling 2 dice whose sum is 5 would be these 4 outcomes divided by the 36 outcomes in the sample space, and this fraction reduces to 1/9 because these numbers can both be divided by 4. Okay, let's look at part C. Find the probability of rolling 2 numbers whose sum is greater than 7. Okay, we'll look at this diagonal right here. If we start in this upper right corner, 1 plus 6 is 7. And then if we go down diagonally, 2 plus 5 is 7, 3 plus 4 is 7. It looks like if we start in the corner and go down diagonally, all of these add up to 7. And then everything to the right of that adds up to something more than 7. So the outcomes that I have circled here in red are the ones whose sum is greater than 7. You can see, for example, 2 plus 6 is 8, 5 plus 5 would be 10. You can see that all of these add up to a sum that's greater than 7. All the ones to the left either add up to 7 if they're on this diagonal, or if they're to the left of that, they add up to something smaller than 7. So these are the only ones that will work. And how many are there? Remember, we're counting pairs of dice here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the probability of getting a pair of dice whose sum is greater than 7 would be 15 divided by 36. Now both of these numbers can be divided by 3. So when we reduce this fraction, we will come out with 5 divided by 12, 5/12. And then for part B, find the probability of rolling doubles. Well, let's go back to our sample space and find all of the doubles. Here we have 2 1s, 2 2s, 2 3s, and so on. And so these are the only doubles that we have out of all 36 possibilities. And so the probability of rolling doubles would be 6 divided by 36, which reduces to 1/6. And let's keep going with example 5 here. So this is part E. It says find the probability of rolling 2 numbers whose sum is 11. Well, now we've done a couple where we had to find a particular sum. So if you would like to pause the video and try this on your own, that's a great idea. Okay, now let's do it together. So we're going to go back to the sample space and find all the pairs that add up to 11. And we know that all of the pairs that do this will be on a diagonal. So if we find one, we can find them all. So let's start here in the lower right corner where we can see that 6 plus 6 is 12. If we go up 1 from there, 5 plus 6 is 11. And then on the diagonal, the only other one that will work is the 6 and the 5. These are the only 2 pairs that add up to 11. Anything to the left of these numbers is going to add up to something too small, and we know that the 6 plus 6 is going to be too big. So the probability of rolling 2 dice whose sum is 11 would be these 2 outcomes divided by 36, and this fraction is going to reduce to 1/18. For part F, find the probability of rolling 2 numbers whose sum exceeds 12. Okay, when we go back to the sample space and look, the largest outcome we can get has a sum of 12. There's no way to roll a number bigger than 6, so there's no way that the sum can be bigger than 12. So the probability of rolling a pair of dice whose sum is greater than 12 is going to be 0 divided by 36, which is just 0. In other words, that is an impossible event. And then for part G, find the probability of rolling 2 numbers whose sum is less than 13. Well, when we go back to our sample space, all of the pairs have a sum that is less than 13. So all 36 outcomes here are part of this event. And so the probability of rolling a pair of dice whose sum is less than 13 is 36 out of 36, which simplifies to 1. This is a certain event or a guaranteed event. If you roll a pair of dice, it is 100% certain that the sum of the 2 dice will be less than 13. Now let's switch over and talk a little bit about empirical probability. So we've said before that theoretical probability is based on a set of equally likely outcomes and the number of elements in the set. On the other hand, empirical probability applies to situations in which we observe how frequently an event occurs, because it could be that all of the outcomes are not equally likely, or it's also possible that we don't know all of the outcomes, but we can observe how frequently one of the outcomes occurs. And so when that happens, we have to just calculate probability by observation. So here's what we do. When we're computing empirical probability, we say the empirical probability of event E, which is written P of E, is just the observed number of times that E occurs divided by the total number of observed occurrences. And a lot of times when we calculate empirical probability, there's a table involved. So here's example 9, and it says, in 2020, there were approximately 264 million Americans aged 15 or older. The table shows the distribution by marital status and sex of this population. Numbers in the table are expressed in millions. Okay, they almost always tell us that the numbers in the table represent millions or thousands or something like that, but it doesn't matter. We can really ignore the millions because a million divided by a million is 1. So the millions are going to cancel out anyway. All we have to do is work with the numbers that they give us. Now watch it, because a lot of times your table will contain a row that totals up everything in the columns and a column that totals up everything on the rows. So for example, if you need to total up the number of males here, you don't add 68 plus 46 blah 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 plus 128, because the last column represents the total. They've already added these numbers for you, and these numbers add up to 128. And the same thing for this bottom row. The number of divorced people is not 11 plus 15 plus 26. It's just 26 millions, of course, because 11 million are male and 15 million are female, and so the total number of divorced people is 26 million. Okay, so part A. If one person is randomly selected from the described population, find the probability that the person is divorced. So what we need to do is take the total number of divorced people and divide it by the total number of observed people. So the total for the whole table is 264 million. Okay, so the probability of observed divorced people is this 26 million right here. And the total number of observed people is this 264 million right here. So the probability that we randomly select a divorced person is 26 million divided by 264 million. Remember, we don't have to write the millions because they would cancel out anyway, and we're going to get a decimal value for this. Now, they will have to tell you when you do your homework assignment how many decimal places to keep, so watch for the instructions that tell you how many decimal places to round to. Here, we are going to round to 2 decimal places. So when I punch this into my calculator, 26 divided by 264, this is what I get. And if I want to round to the second decimal place, that would be where the 9 is, I would look at the 8 and I would say, okay, that's 5 or more, so this 9 is going to go to 0, and just like an odometer on a car, when this 9 rolls over to 0, this 0 will roll over to 1. So if we're rounding to 2 decimal places, then our answer is approximately 0.10. Let's look at part B. If one person is randomly selected from the described population, find the probability that the person is female. Okay, so the females are right here on this middle row, and we can see in the table that the total number of females is 136 million. And then the total number of people is still 264 million. And so the probability of randomly selecting a female would be 136 divided by 264. And on the calculator, this is what we get, 0.5151 repeating. And again, if we want to round to 2 decimal places, we go to the 1, We look at the next digit, which is a 5, so that's going to cause the 1 to change to a 2, and so our probability is approximately 0.52. In other words, the probability of randomly selecting a female out of this group is a little better than half. And part C, if one person is randomly selected from the described population, find the probability that the person has never been married. Okay, so we go to the never married column. The total number of people who have never been married in this table is 87 million. And the total number of people in the table is 264 million. So the probability of randomly selecting someone who's never been married is 87 divided by 264. And when we get our calculator value, we get 0.3295 and so on. And if we want to round to 2 decimal places, we look at the third decimal place. That's big enough to cause this 2 to change to a 3. And so this probability is approximately 0.33. In other words, the probability of selecting someone who's never been married is approximately 1/3, because 1/3 exactly would be 0.33333 repeating, and this is very close to that. And finally, part D. If one person is randomly selected from the described population, find the probability that the person is male. Okay, so we go to our table, and we get the total number of male people, and that's going to be 128 million. And of course, as we've seen before, the total number of people was 264 million. So the probability of randomly selecting a male out of this group is 128 divided by 264, and that decimal value is going to be 0.4848 repeating. And so if we round to the second decimal place, then that probability is approximately 0.48, or just under 1/2. Okay, you guys, that is a quick look at the basics of probability, and we are going to continue working with probability in the next section, which will be section 11.6. So I'll see you then. Bye.